Welcome to my CS50 final project. My name is Teo, and this is my program FTIR Buddy, a Python program designed to assist with FTIR spectroscopy. Very briefly, FTIR spectroscopy is an analytical technique used to investigate transitions within rotational and vibrational states of molecules. This is done with light or electromagnetic radiation. The Fourier transform allows us to take information from interferograms in the time domain to the frequency domain, and then we can relate the observed spectra to physical properties of the molecule, which requires quite a lot of calculations, which is where this program comes in handy. From the FTIR, we will get a spectrum that looks something like this, where we have peak frequencies corresponding to specific transitions. We can use these equations here to index those equations and produce a CSV file with the peak frequencies corresponding to specific numbers. This is great because FTIR Buddy can read a CSV file very easily. We then want to calculate all these specific parameters. These are spectroscopic parameters that I won't get into the details because I only have about a minute and a half left in this video. But you can go look at ChemLibreText or something like that for an awesome explanation of all these parameters. One of the more challenging aspects of this program was doing the error propagation, which is really important. To do so, I used the general error propagation scheme. I defined a function within Python that'll accept a mathematical function which we define, two parameters which we define, as well as the uncertainty of those two parameters and the value of those two parameters. After making sure ints and floats are where they need to be, we differentiate our function, mathematical function q, with respect to x1 and x2. We then substitute in the values if need be, and then reduce them. And then also we feed them into a sum of squares square rooted formula and return the value. Another cool aspect of this program is doing some statistical mechanics where we create a plot estimating relative peak intensities based upon the rotational constant b, which we have calculated in this program. So in this function relative peak, we feed in the rotational constant as well as the molecule itself. We calculate at 3 different temperatures 10 different rotational states and save them in separate lists and then plot those separate lists in another function called relative plot. And lastly, we'll go ahead and run project.py. It'll first prompt us to enter the molecule we're investigating. Here I'm going to enter HCl. It'll then ask us for the isotopes of each of the atoms within the molecule. I'll go ahead and put in 1 for hydrogen and 35 for chlorine. It would like a first fundamental frequency, which we can get from literature values, with the associated uncertainty. And lastly, it would like the CSV file containing the data for the data fit. And the first thing that pops up is the data fit. So we have the peaks transitions in the blue dots, and the orange line is the fit from which we extract parameters from for further calculations. The next plot that comes up is the relative population plot, which we talked about earlier for specifically our molecule. Next, we have all of our calculated parameters. So reduced mass, bond lengths, spring constant, all with associated uncertainty and all rounded with the scientific convention.